Why do we need direct air capture and how chemical engineers can help making this technology viable? I'm Dr. David Hanak and I'm going to answer this question during this episode of Net Zero Academic. First of all, let me thank you for everyone or for all of those who supported my work via coffee, buying me a coffee on coffee.com. You can see the link somewhere over here, I guess. And I really appreciate this because it gives me a drive and motivation to produce even more value for you. And I do work on some content just for my subscribers and just for my supporters. So if you've got any questions that you want me to answer, please do let me know. I'm happy to provide a lecture or something like this on that. This is really exciting time to be in this area, in the area of sustainability, net zero, and in general energy transition, mostly because there's so many different innovations happening, to be honest. And it's difficult to find your way through it sometimes. And that's where I come in. That's how I can help. So today's topic, and I already mentioned that last week, today's topic is direct air capture. And there is a lot of discussion about this technology. Lots of people hate it, people love it. There are some people in between as well, but usually there is this extreme reactions to it. Personally, I do think it's interesting technology from chemical engineering point of view, mostly because it's very difficult chemical separation process, right? You've got very small concentration of CO2 in the air, small from the chemical engineering perspective, not from the climate perspective. And then if you want to capture that, it's really difficult to do. So it's really difficult challenge to tackle. That's why it's exciting for me and for my students. So today I want to talk about a little bit why do we need direct air capture and what are some of the key challenges that chemical engineers can help tackling, can help with solving. And then I've got a special announcement at the end of that of this episode, and yeah, so stay till the end so that you can make the most of it. I'm going to talk about, provide you with the overview of direct air capture right now. So this is something I've talked through with my colleagues at Nordic DAC Group. If you want to follow them, check out their profile. They do really cool stuff. So if I just switch to my presentation right now, you'll be able to see my slides, right? If you're listening to this, I will provide a link to slides or a link to the video in the description. So today I just want to give you an overview of direct air capture, say why we need that and what are the key challenges. So why do we need that, right? So if you follow some of the largest organizations that provide reports in direct air capture or in general in greenhouse gas removals, they will basically identify that we do need negative emissions. We do need negative emissions so that we can offset some of the difficult to abate industries. Of course, with power and industrial decarbonization, we would reduce our emissions as much as possible. And we can do that with fuel switching, with carbon capture storage, with renewables. Of course, we can do that within industry at the scale. But, there are some small industries and niche industries where it will be extremely difficult to decarbonize because CO2 might be a part of the process. You might have other emissions than CO2, like methane emissions, or all of those other greenhouse gases that are present. And so to balance this out and achieve net zero, that's why we would need actually the net zero emissions. And according to the Royal Society, so that is a little bit old report already, but it still is valid. So according to Royal Society, we would need at least 800 gigatons of CO2 to be removed from the air by the end of the century so that we can maintain 1.5 degrees Celsius temperature increase. So this is quite a lot, right? And we've got all different options for greenhouse gas removals. We've got biological options, we've got planting trees, but in terms of the scale and in terms of how much carbon dioxide you can actually remove per amount of per amount of land, per amount of water that you consume, those solutions might not be might not give us the opportunity to scale up those removals to the level that we need. So that's why we think about engineering ideas like direct air capture or BECCS, biomass carbon capture and storage, where we can actually put together a plant that will suck CO2 out of the air and then will use, of course, energy. Yeah, this is the main challenge with that technology, energy consumption. But from the technical point of view, we can do this, right? So that is the main rationale why we need negative emissions or greenhouse gas removals. It is not meant to replace, fossil fuel reductions. We do need to stop using fossil fuels as soon as possible. Of course, we will not stop that overnight, but offsets using greenhouse gas removals should not be used for, as a license for companies to operate under the fossil fuels. So it's not the license to use fossil fuels. It's something that we may need in the future, or that we will need in the future, to balance our emissions so that we become truly net zero economy. So looking at the technology overview, so direct air capture is, of course, a chain of process that we would need to implement. It's not a standalone technology. So we do start with taking CO2 out of the air. So that is one of the most difficult things that chemical engineers can tackle, right? So this is mostly because we have very low concentration of CO2 in the air from the chemical engineering perspective, and you do have to use very strong solvents that will actually capture that CO2 or remove that CO2 directly from the air. So contacting air and solvent, by achieving high contact area, you can, of course, improve that reaction. And that's where chemical engineers have an opportunity to apply their skills and develop new contacting devices that would reduce the volume of the system, but also maximize the uptake of CO2. So that's the first step, right? The first step is you capture CO2 from the air. You capture it by a solvent, a liquid material, or sorbent, a solid material. And that material needs to be regenerated, right? So you don't want to just have a one-through system. You want to make sure that you regenerate the system and have a kind of circulation of the solvent or sorbent. So that is another issue, because to regenerate that sorbent or solvent, you do need energy. Either that's electrical energy or whether that's heat, high-grade, low-grade heat. That is the issue, another issue of direct air capture, because you do need quite a lot of that heat to reclaim CO2. There are other options. There are options to reduce that energy intensity, but this is another area where chemical engineers can focus their attention to. Once the CO2 is released, we can either store it underground, which is reasonably okay idea, I think, in the mid-term kind of way. But I believe that the best option for that CO2 is to be used for manufacturing of some of the blocks or key crucial chemicals that we use in our economy, whether that's methanol, whether that's DME, whether that's synthetic fuels. So depending on how the CO2 is used, whether that's used for materials that are not burnt, then we would achieve permanent CO2 locking, and as a result, that process will be carbon negative. But if we use CO2 for synthetic fuels production, at best we could become carbon neutral. Okay, of course, if we use synthetic fuels, the cost of that will increase. That will have implication on other parts of our economy. So that's why it's crucial for direct air capture to become as cheap as possible. Hence, we want to make it as small as possible. We want to make it as energy efficient as possible. The benefit of that, of course, is if you produce synthetic fuels that are carbon neutral, you can replace the use of fossil fuels in aviation, transportation, and so on. So that is the main benefit. So there might be, a trade-off in terms of economics, but in terms of environment, it should be better off. But again, I'm not trying to promote this technology because some people said that I'm trying to promote that technology. It is one of the technologies that we might need to deploy. It's not the ultimate, it's not the silver bullet to climate change. It is just exciting technology that I've been working on for the past couple of years. I do believe that we need that to some extent, but there are other options that we have to consider. Anyway, going back to the topic, you can see that chemical engineers will play a quite crucial role in here, because they would look into how you can take CO2 out of the air in the most efficient way, how you can reclaim it back from the solvent, but also how you can convert that into something useful. So basically, you're trying to make CO2 that we consider as a waste, we try to convert that into a valuable product that could help us decarbonize our economy. And there are a couple of options there, right? So we've got carbon engineering, which is high temperature system, basically based on the base of a craft process, for example, in pulp and paper industry. It uses natural materials, which is quite promising, sodium or potassium hydroxide. We've got dual loops over there. I would not go into details, but it uses existing contactors, uses existing equipment. The downside of that, in my view, is that it's high grade temperature regeneration. So basically, to regenerate sorbent, you need high grade heat. And in many cases, that's provided by oxy-combustion of fuel or fossil fuel. So you can see that to take away CO2 from the air, you use fossil fuel, and that in terms of the carbon balance, this is still carbon negative, but to capture basically to capture 1 ton of CO2, you need to spend something about 0.4 tons of CO2 in terms of the fuel combustion. So overall, you would capture about 0.6 tons of CO2 as a net emissions, which is still positive. I mean, it's still carbon negative, but it is, well, if this technology was run by renewables, for example, solar and so on, assuming you can continuously operate that, that would be better, because you would be capturing 1 ton, getting about 95% efficiency. Of course, with solar, there is this variability of availability of heat, so that poses additional challenges. There's no perfect solution, right? So this is one option. Another option is low temperature direct air capture, where you've got a Climeworks or global thermostat. They use amine-based sorbents. So instead of using liquid solvents, like in case of carbon engineering, Climeworks and global thermostat uses amine-based sorbents, solid materials, solid particles, that are regenerated at lower temperature, lower pressure. So you can use either temperature swing or pressure swing adsorption in this case. So the temperature is much lower. I guess it's about 80 to 100 degrees Celsius. So you can use some waste heat where it's available, of course, if it's available. So some of the Climeworks demonstration in Orca in Iceland, they use geothermal energy to regenerate sorbent. And that is quite a nice, in my view, this is very nice kind of integration between direct air capture and renewable energy. So basically, when you look at the comparison of those technologies, you can see that you've got the high temperature technologies for now, which is carbon engineering, 900 degrees Celsius regeneration. Well, it depends on the sorbent that they use to regenerate. It could be 850, it could be 950, and so on. But yeah, the thermal energy requirement might not be as high, but the high temperature causes an issue here as well. In terms of Climeworks and global thermostat, they need lower grade heat, which is about 100 to 85 degrees Celsius, but the amount of heat might be quite high depending on how you can heat integrate that process. In terms of cost of capture, of course, this is the main challenge, right? So in terms of how much they estimate the future price would be, we could go below 100 euro per ton of CO2. This is quite promising, I think, because it's almost equivalent to what we see in the EU ETS market right now, which is, with the prices are above 95 euro per ton of CO2. So basically, if you can do it now with those technologies, those technologies should be getting paid. If direct air capture was included in the EU ETS. But for now, the prices are more about 400 to 600 euro per ton of CO2, maybe 250 for Climeworks and global thermostat. So it is still an expensive tech that we could plug in and produce CO2. Some of the areas where we need to look into in terms of the development. So you can see that the scale, that's my personal opinion, where basically the scale of a single unit might be bigger for carbon engineering, while the Climeworks unit and global thermostat unit would be smaller, I think. Of course, you can put more modules there, but in terms of single unit, I think carbon engineering will be a bigger scale. In terms of electricity grade, energy grade, of course, lower grade is better because it needs less energy in principle. And you have opportunities to integrate that with low temperature solar, low temperature waste heat recovery where available. Capital cost, of course, the bigger the scale, the bigger capital cost. So yeah, fairly comparable, and so on, right? So there are lots of challenges over there, lots of opportunities for chemical engineers where they basically can help us find solutions to decarbonization or making this technology cheaper and less expensive. But these are the potential markets that I wanted to show you where you can use CO2. And in many cases right now, we mostly use CO2 for EOR, enhanced oil recovery. That is a way to pay for that project, basically. Not very sustainable from the life cycle assessment because you would produce a net amount of CO2 when you use CO2 to produce more oil, and that oil is later combusted. So basically, the net carbon balance doesn't. It just implies it's not that sustainable. Of course, this is a way to pay for the direct air capture projects in some cases, where you basically demonstrate that technology, and then you can move to a more sustainable options. Of course, so that could be a way. But of course, there are different routes where you can utilize CO2 for production of chemicals like methane, methanol, or gasoline or jet fuels. You can produce chemicals. One of the most commonly evaluated chemical is methanol, because it can be converted as it is an intermediary for production of other chemicals within the petrochemical industry. CO2 can also be used for building materials, right? So there's a couple of companies that use CO2 to produce cement, concrete, and so on, and aggregate. So that is another way to lock CO2 in permanently within that material. Finally, we have new uses of CO2 where you can use it as a non-conversion. So you use it as a solvent, or you use it as a heat transfer fluid. One of the applications that I find interesting and really exciting is supercritical CO2 cycles, where you basically use CO2 as a working media in the power generation system. These tend to be more efficient than conventional Rankine cycles based on steam, water cycles. The issue might be the leakage of CO2 and the turbo machinery and so on. But of course, there is a further development to be made in this area. So you can see that for chemical engineers, there are opportunities across the entire supply chain of direct air capture, from the contacting CO2 with in the air with the solvent, regenerating CO2, but also what to do with that amount of CO2 in the most reasonable way so that we create a value out of this rather than just treat it as a waste. So these are the questions that I hope the future chemical engineers that I work with will help me answer. And that is the end of this presentation. Just wanted to emphasize that direct air capture is a pretty interesting technology, and there has been quite a lot of development in this area over the past couple of months, couple of years actually. And I'll be sharing my review paper fairly soon. It's accepted by the journal, but we submitted the proof to the journal as well. But of course, it takes a little bit time for them to process it, of course. So hopefully that will be out soon, so you would be able to understand the full picture of what's going on in direct air capture, what are the state-of-the-art technologies, materials, processes, what are the socio-political implications, and so on. So I'll be sharing that once it's available. But now I wanted to announce that I'll be running special issue of Clean Energy Journal. So my colleagues at Clean Energy Journal, they invited me to run a special issue on direct air capture for the circular carbon economy. And I'm hereby encouraging you to submit your work to Clean Energy, which is published by Oxford University Press. So the main idea behind that special issue is to basically have a look at what are the new ideas in direct air capture. What work are you doing in, across different stages of direct air capture, whether that's new materials, new processes, new utilization options. I'll be happy to see any, not any, good high quality submissions in direct air capture for circular carbon economy. The good thing about publishing in Clean Energy is that it's the open access journal published by Oxford University Press, and it has no APC, so there is no fees associated with getting your work published as an open access paper. The impact factor is not there yet, but being a member of a editorial board, I can tell it will be quite promising. I hope we get it fairly soon. So this is the announcement I wanted to make, that I'm opening the call for papers for this special issue of Clean Energy, and I do hope to see your submissions fairly soon. If you've got any question about this special issue, please do refer to the website. I'll put the link below, but also feel free to contact me either at contact@drhanak.com or via LinkedIn or any other platform directly. Okay, so this is the announcement I wanted to make. I hope it's exciting. It's really exciting for me because I do believe that we do have to share our research openly. We do have to make sure that the research is open access, and we need to find a way to make publishing a little bit more sustainable for everyone. Okay, so this is pretty exciting for me, and I do hope you find it exciting as well. I like to finish those episodes and live sessions with Q&A sessions. So if you've got any questions that you want me to answer right now, please leave them below this video, and I will have a look at whether you've got any questions right now, just to see if there are any questions, right? I don't have any questions that I haven't received any questions before this episode, which is sometimes it happens, sometimes it doesn't, but I do like to keep it fresh. I do like to keep the Q&A session live. I can see a couple of comments there. Let me just quickly have a look. Thank you, Wagner. Nice to see you. Nice to see you attending. Let me just translate that a little bit, because I'm not very proficient in that language. Thank you, Jonathan. Thank you, Jonathan. Okay, so Jonathan asks whether will carbon capture will ever be scalable? This is a very good, very good question. It really depends. Okay, it really depends on where we want to put this. I mean, carbon capture and direct air capture, completely different business models if we look from the business perspective. So carbon capture, we reduce emissions by allowing using fossil fuels. So basically, there will be a penalty on operation of the company because you will need to pay for the additional capex, opex of the carbon capture plant. Your power output will decrease depending on the technology that you use. But the carbon capture, I guess it could be scalable if we find a way to use that CO2, if we find a way to either store it or use it in a sustainable way. In terms of direct air capture, I do think that it is a potential technology. Of course, we can plant trees, but we cannot plant trees at the scale that is needed, unfortunately. So we do need to use all options we've got to keep the temperature increase within 1.5 degrees Celsius. I'm not saying that we shouldn't be planting trees or we shouldn't be looking into other technologies. We need to take a portfolio approach. Every little helps, right? So if we find a way to do direct air capture in the feasible way, of course we would offset a part of it, part of the removals with direct air capture. Of course, wherever we can do tree planting, we would do that. But planting trees in places where they don't grow right now might not be the most feasible option. Okay, so I think, well, carbon capture could be scalable. It just depends on how we can explain the business model and how we can ensure the potential risk associated with CO2 storage can be mitigated. Hope this helps. Happy to take it off of the live as well. I'm always happy to discuss this, to be honest. Let me try to see what Wagner. I don't think I can. Right, Wagner. I'll answer to your question offline because it seems there is an issue with translation of your question. But I do hope that it will be. Yeah, I'm always happy to answer. Jonathan, about energy return on investment. This is something I need to work out. I haven't looked into energy return on investment for direct air capture yet. But if we look at energy return on investment, then we would all want to invest in nuclear energy because that brings the highest energy return on investment, while renewables bring very small energy return on investment. So, energy return on investment is a good metrics in terms of comparison, but we need to look at a bigger picture here as well. Right. If there are no other questions, we'll basically take this this episode to a close. So thank you everyone for attending. I know it was a little bit of an ad hoc live session. I didn't announce that properly last week, but it's been quite a busy period over the past couple of weeks. I do hope that you enjoyed. I do hope that you see the value that direct air capture can potentially bring to the table. And hopefully, as if you're a chemical engineer, you can see that what sort of challenges are there and how you can contribute towards solving those with your design skills and your engineering skills. Thank you everyone for joining this live session, and I will speak to you soon. Thank you.